so far, you walked through their simplest examples of their overbearing scattering, where there is just one simple turning point in the complex plane. Today, however, we'd like to discuss a more advanced problem. And the key difference of this problem is that we'll see that the structure of the wave function near the turning point is different because near the turning point will be present another important point, namely the pole of the potential. And this potential is quite, I would say, famous in quantum mechanics. It's 1 over Cauchy squared. And for those who are not familiar, this is an exactly solvable potential. And the key point is that if you solve a scattering problem in this potential, there are some values of their potential well such that of the depth of the potential well such that their scattering becomes reflectionless and is independent. And these values of U0 are independent of the energy of the incident particle. And let's see if we could recover that features in the semi-classical approximation in the overbearing scattering, addressed via this complex plane method. So here is the profile of our potential. And we'll address the case, well, first of all, our energy is large enough so the semi-classical treatment is applicable. And second, the depth of the potential well is supposed to be rather small. It's much smaller than the square root of the energy and this semi-classical expression, 1 over ma squared. And as you probably noticed, I put here h bar equals 1 for the rest of this lecture. OK, so now let's see what's going near their turning point. So here is the equation for the turning point, where x0 is the turning point. And from the second condition, it follows that the depth of the potential well is actually much smaller than the energy of the incident particle. So now let's look at our equation for the turning point. We see that the left-hand side of this equation is much greater than the amplitude of the right-hand side. That means that the denominator should be very small to compensate for the difference between the amplitude of U0 and E. And this entails in particular that x0 point should be close to the 0 of the Cauchy of this denominator. And hence, we can solve this equation. And what we get is quite unsurprising. So as you remember, we are interested only in the turning points which are positioned in the upper half plane of the complex plane of x. Obviously, because there are many of them due to the periodicity of the Cauchy function. And here is the turning point, which is the closest to the real axis. So it's I pi by 2a plus minus. Let me have a look. A arc sinh of lambda, where lambda is a square root of U0 over E. So this is a small parameter. So this arc sinh can be expanded. And as a result, we have well, obviously, the problem is, since our turning point is very close to the 0 of the denominator, that means that our turning point is actually close to the pole of the potential well in the complex plane. And now we ask ourselves a question: is it legitimate to expand their potential energy near this turning point? Let me actually show you the precise picture in a complex plane. So here is our x complex plane. Here is the pole of the potential well, which is we denote x1. And here are two turning points. And what we did before, we always expanded the potential well near the turning point. So we used this expansion, so delta x was much smaller than the characteristic scale of the potential, which is a in our case. But since lambda is small, the important x here, they actually circumvent, when we circumvent this, the region of important delta x around this, say, the right-hand side turning point, then the pole itself enters this region. And the whole expansion, Taylor expansion of the potential near this turning point is illegitimate. So the right expansion would be the Laurent expansion near the pole, rather than the Taylor expansion near the turning point. So that's why sometimes this kind of reflection, or this kind of case, is called the coherent reflection from the pole and the turning point. Right, so now let's perform, instead of the Taylor expansion of the potential, let's perform the Laurent expansion of the aforementioned potential near the pole. And here it goes, so it's minus So this is the correct Laurent expansion. As you see, we retained the regular term and u naught over 3. And then we can write down the corresponding Schrödinger equation near this pole. So here it goes. Minus 1 over 2m psi prime prime, and plus our potential. And of course, instead of this x, it should be the delta x, the difference between their pole and the corresponding x. Sorry. And we call it s. Right. So now let's introduce some more suitable notations. First of all, we introduce the wave vector, which is 2m plus u naught over 3. And kappa squared. And in this notation, the Schrödinger equation becomes the standard differential equation. So here is our final differential equation, Schrödinger equation, near the turning point or near the pole of the potential well. So first thing that we see that it's slightly reminiscent of the Bessel equation. And indeed, it can be reduced to a Bessel equation. However, in this case, I'd like to study the full analytical structure of this equation rather than teaching you how to use standard reference books. So instead of addressing the corresponding asymptotics of the Bessel equation, we'll see how the corresponding transmitted and the reflected wave arise from the analytical structure of this differential equation. So first of all, we see that it has this quadratic term, and we get rid of this quadratic term and reduce this equation to the equation with linear in s coefficients. In the standard manner, we look for asymptotics at large and small values of s, and then we substitute psi with more suitable ansatz. Right, so first, asymptotics at large s. It's trivial, we just discard term kappa squared a squared and get the expected differential equation, and the asymptotics are simple plane waves. For small s, well, for small s we discard the first term in these braces, and what we get is simply s squared psi prime prime equals kappa squared a squared psi. So these are small s. And again, this equation has a simple solution which can be thought in the following ansatz. And now we may write equation on this mu. It's mu squared minus mu equals to kappa squared a squared. And as a result, mu equals 1/2. And we choose for brevity, for simplicity, plus sign, positive mu. And our substitute would be now as follows. So we'll seek for the solution of this differential equation in the following form. Psi is equal to s to mu e to I ks times new function phi of s. And for this function phi of s, we'll have our differential equation with linear coefficient. And let's study it on our next slide.